Welcome back to Basic Electronics. In this lecture, we will look at another logical block, the encoder. After that, we will start with a different class of digital circuits, namely sequential circuits. We will see in what way they are different from the circuits we have considered so far. We will take up the most basic block of sequential circuits, that is the latch. Okay, let us begin. Let us discuss encoders now. We have m inputs A0, A1 up to AM-1 and n outputs O0, O1 up to On-1. And this is how it works. Only one input line is assumed to be active. That means only one of these is active, all others are inactive. And then the binary number corresponding to that active input line appears at the output pins over here. Now let us try to figure out the relationship between m and n here, and let us take an example. Say n is equal to 3. That means we have 3 output pins, say O0, O1 and O2. And how many different binary numbers can we make up with these 3 variables? The answer is 2 raised to 3, that is 8 different binary numbers. And each of those binary numbers can correspond to one of these input lines. So therefore we can have a maximum of 2 raised to 3 or 8 input lines. Only then we can have a one-to-one correspondence between the inputs and the outputs. We will take some examples and then this will become clear. Alright, so here is an 8 to 3 encoder example. We have 8 input lines and 3 output lines. And here is the truth table. And we will of course assume that only one of these input lines is active. And these are all active high pins, so therefore active means 1. In this row, for example, the active pin is A0. Now the output that corresponds to this particular combination, that means A0 being active and all others inactive, is 0, 0, 0. For this combination, where A1 is active and all others are inactive, is 0, 0, 1 and so on. In the last row, we have A7 as the active input line, and corresponding to that we have an output of O2 equal to 1, O1 equal to 1 and O0 equal to 1. So this is an example of an 8 to 3 encoder. In this example, note that only one of the input lines is assumed to be active at a given time, and therefore we have only one high pin here in any of the rows. That means we will see only 1, 1 in any of the rows. The question that arises is, what if 2 input lines become simultaneously active? Now to handle that situation, we have something called priority encoders, in which a priority is assigned to each of the input lines, and then that is used to decide the output if 2 pins or more than 2 pins become simultaneously active. Let us look at an example of this. Here is the 74147 decimal to BCD priority encoder. We have 9 input pins, A1 bar, A2 bar up to A9 bar, and these are active low as indicated by these circles. We have 4 output pins, O0 bar, O1 bar, O2 bar, O3 bar, and these are also active low. Here is the truth table, and let us now look at these rows one by one. In the first row, all input pins are 1, that means inactive, and all output pins are also 1, that means inactive. So this output number corresponds to the binary number 0000. Alright, let's come to the second row. In the second row, A9 bar is low, that means active, and there are these don't cares in all other columns. That means it doesn't really matter what these are, and A9 bar will be given a priority. So this input pin is active, and the corresponding output pins are 0, 1, 1, 0, and since the output pins are active low, this number actually corresponds to the binary number 1001, and that is decimal 9. So there is a correspondence between which pin is active here and the corresponding binary number here. Let us note that in all subsequent rows here, A9 bar has been shown as inactive, and that is because it has the highest priority. And if this was 0 anywhere, then it would not matter what all these other entries are, and the output would then be this one. Alright, now let us take this row. Here A8 bar is active, and the corresponding output is 0111, which is the binary number 1000 or decimal 8. Similarly, when A7 bar is active, we will find that the output corresponds to the binary number 0111, that is decimal 7, and so on. So let us summarize. Note that the higher input lines get priority over the lower ones. That means A9 bar gets priority over all these others. A8 bar gets priority over A7 bar, A6 bar up to A1 bar, and so on. For example, A7 bar gets priority over A1 bar, A2 bar, A3 bar, A4 bar, A5 bar, and A6 bar. If A7 bar is active, that is low, the binary output is 1000, that is 0111 inverted bit by bit, and that corresponds to decimal 7, and that is irrespective of all of these other input pins. So the lower input lines therefore are shown as don't care conditions. Digital circuits can be broadly classified into two types: one, combinatorial circuits, and two, sequential circuits. We now want to discuss sequential circuits, but first let us make a few important points. The circuits we have seen so far, gates, multiplexer, demultiplexer, encoders, decoders, are all combinatorial in nature. That is, the output depends only on the present values of the inputs and not on the past values. For example, let us consider a multiplexer. Now the present value of the output for a multiplexer will only depend on the current or present values of the input lines and the present or current values of the select lines. And it really does not matter what happened in the past, what values these input lines or select lines had in the past. That simply does not matter. So that is a feature of all combinatorial circuits. On the other hand, in sequential circuits, the state of the circuit is crucial in determining the output values. For a given input combination, a sequential circuit may produce different output values depending on its previous state, and we will see several examples of that. So for a sequential circuit, two things are important. One, the present values of all its inputs, and two, the state of the circuit. Now what is the meaning of state? That we will see as we go along. In other words, a sequential circuit has a memory of its past state, whereas a combinatorial circuit has no memory, and that is the big difference between the two. And finally, sequential circuits together with combinatorial circuits make it possible to build several useful applications such as counters, registers, arithmetic logic unit or ALU, going all the way to microprocessors. Alright, so here is a simple sequential circuit, and it's called a Nand latch. Nand because it uses NAND gates, and latch, we will see why it is called a latch. It's also called RS latch, and the meaning of this terminology will also become clear very soon. Alright, so here are two NAND gates, gate 1, gate 2. Two inputs, A going to the first gate, B going to the second gate. And the second input of the first gate is coming from the output of the second gate, like that. And the second input of the second gate is coming from the output of the first gate. So our inputs are A and B, and the outputs are X1 and X2. And now we want to prepare a table of the inputs and the outputs. Let us start with A equal to 1 and B equal to 0. So we have 1 here and 0 here. And we don't know what the other input of this gate is yet. But we do know that if this is 0, then X2 is going to be 1, because any one input of a NAND gate being 0 implies that the output must be 1. So we can say that X2 is 1. And now we come back to this gate. Its first input is 1 and this second input is also 1. And we know therefore that X1 must be the NAND of A and X2, and that is 1 and 1, and bar of that is of course 0, like that. So when we have A equal to 1 and B equal to 0, we have X1 equal to 0, X2 equal to 1. So that entry is now completed. Alright, next let us take A equal to 0 and B equal to 1. So this is 0 and this is 1, and by the same logic X1 would now be equal to 1 and X2 would be NAND of 1 and 1, that is 0. So that is the second entry. A equal to 0, B equal to 1, X1 is equal to 1 and X2 is equal to 0. Now let us consider A equal to B equal to 1. So 1 here, 1 here. And now X1 is A X2 bar, A X2, and of that, and then the not of that, so A X2 bar, that is X2 bar because A is 1. Similarly, X2 is B and X1 and not of that, so that is B X1 bar, and because B is equal to 1, it is equal to X1 bar. So what it implies is that X1 and X2 must be inverse of each other. X1 is X2 bar, X2 is X1 bar. And this relationship is indicated here by writing X2 bar here and X1 bar here. So X1 is the same as X2 bar, X2 is the same as X1 bar. Now whether X1 is 0 or 1, we don't know, and let us take two cases. For example, if X1 was 1 earlier and X2 was 0, then that situation will continue to hold because it does satisfy this relationship. Similarly, if X1 was 0 and X2 was 1 previously, then the circuit will continue to hold that state. So both of these are possible. We can have X1 equal to 1 and X2 equal to 0, or X1 equal to 0 and X2 equal to 1. And which one of these will actually happen depends on what was X1, what was X2 before. And in the table for the latch, we write this observation as previous. That means whatever was the previous condition, either this one or that one, will continue to hold. And that is why this circuit is called a latch, because in a sense the circuit has latched in the previous state. It is not changing. Alright, one last point. For a equal to b equal to 0, x1 and x2 are both 1. If we have 0 here, that means x1 is 1. If we have 0 here, that means x2 is 1, and that is irrespective of this other input. So for a equal to b equal to 0, x1 and x2 are both 1. But this combination of a and b is not allowed, and we will see the reason for that a little later. Alright, so we have written 1, 1 here, but we should bear in mind that this combination is not really allowed. Alright, now these names a, b, x1, x2 are not really used in practice. What we use in practice is some more meaningful names, and let us see what those are. And we start with some observations first. The combination a equal to 1, b equal to 0 serves to reset x1 equal to 0. And why are we saying that? Look at this table. A equal to 1, b equal to 0, x1 is 0. And this happens irrespective of the previous state of the latch. So if you go back one slide, you will realize that this is derived with no reference to the previous state of the latch. Alright. Similarly, the combination a equal to 0, b equal to 1, the second one, serves to set x1 to 1. We have x1 equal to 1 here, and that again is irrespective of the previous state of the latch. In other words, with a equal to 1, b equal to 0, the latch gets reset to 0. This entry here, a equal to 1, b equal to 0, the output of the latch, which we will consider as x1, is getting reset to 0. And with a equal to 0, b equal to 1, the latch gets set to 1. This entry here, a equal to 0, b equal to 1, and the latch output, which is x1, is now getting set to 1. So the a input therefore is called the reset or R input, because when this a is active or 1, then the latch is getting reset. The latch output is getting reset to 0. And b is called the set or S input of the latch. When b is 1 or active, the latch output is getting set to 1. The latch output x1 is denoted by q and x2 is denoted by q bar. And the reason for that is x2 is the inverse of x1 here as well as here. And if you recall, in the last slide we saw that in this third row, when a and b are both 1, x1 and x2 were inverse of each other. Only in the fourth row, x1 and x2 are not inverse of each other, but that row is anyway invalid. So this is our circuit diagram with the new input and output names. R here for reset, S here for set, Q, that is the latch output, and Q bar is the inverse of this. And here is the table that describes how this latch works. When R is 1, S is 0, Q is 0, and it is easy to remember this. R equal to 1 means something is getting reset, and that something is the latch output Q. So Q is becoming 0. S equal to 1 means something is getting set, and Q is getting set to 1 over here. When R and S are both 1, as we saw in the last slide, nothing really changes, and the previous state Q as well as Q bar continues to hold. And the last entry, as we have seen, is invalid, and later we will explain why this entry is considered invalid. Let us now look at some waveforms so as to understand this table better. Here is the R input for the latch. Here is the S input. That is 0 and that is 1. Similarly 0 and 1 and so on. This axis of course is the time axis. Okay. Now in the beginning up to T1, that is, we have R equal to 0, S equal to 1, and the output Q is therefore determined without any ambiguity. So R is 0, S is 1, so the flip-flop is set to 1. So we have Q equal to 1 and Q bar equal to 0. Alright, now at T1 there is a change. R changes from 0 to 1, S continues to be 1, and now let us look at this table and figure out what should happen. So we have R equal to 1, S equal to 1 here, and this says previous. That means Q will stay at its previous value. Q bar will also stay at its previous value, and that is what we see over here. Q remains equal to 1, Q bar remains equal to 0. At T2 there is a change. S changes from 1 to 0. R continues to be 1. So we have R equal to 1, S equal to 0. So let us look at this entry. R equal to 1, S equal to 0. So that resets the flip-flop. That means Q becomes equal to 0. And this happens irrespective of what happened in the past. So Q becomes equal to 0 and Q bar becomes equal to 1. And that continues up to T3 when there is one more change. That is, S goes back to 1, R continues to be 1. So we have R equal to 1, S equal to 1. And therefore Q and Q bar retain their previous values. So previously Q was 0, so it continues to be 0. Q bar was 1, it continues to be 1. All of these observations are listed here, and you can go through that once again if you like. The question we want to answer now is, why not allow R equal to S equal to 0? In this table, for R and S equal to 0, we say invalid here. So the question is, why is this invalid? Alright, so there are two parts to the answer. One, it makes Q and Q bar both equal to 1, as we have seen earlier. That is, Q and Q bar are not inverse of each other anymore. And it doesn't make sense to call this output Q and this Q bar. So that is one reason, but that is a relatively trivial reason. There is a much more important reason, and let us look at that now. Let us look at these waveforms which we saw in the previous slide. And if you recall, we had come up to here in the last slide. We had R equal to 1, S equal to 1, Q equal to 0, and Q bar equal to 1. And now imagine that R has gone to 0, S has also gone to 0. So we have R equal to 0, S equal to 0. Now when R becomes equal to 0, the output of this NAND gate becomes 1, no matter what the other input is. And similarly, the output of this NAND gate also becomes equal to 1 if S becomes equal to 0. So then we have Q equal to 1 and Q bar equal to 1. And that is what is shown over here. Q is equal to 1, Q bar is equal to 1. And that situation continues up to T5. And suppose that at T5, R has gone back to 1 and S has also gone back to 1. So now we have R equal to 1, S equal to 1. What does the table say for R equal to 1, S equal to 1? It says previous. Now the question is, which previous value? Is it Q equal to 1 or is it Q bar equal to 1? And there is a question mark here. What happens in real life is that depending on the delays of these two gates, the latch will finally settle down to either Q equal to 0 or Q equal to 1. That means Q equal to 0 and Q bar equal to 1, or q equal to 1 and q bar equal to 0. So there is some uncertainty about what will happen in this case, and that is why we consider this situation as invalid. Let us summarize. We have started looking at sequential circuits. We have seen how they are different than combinatorial circuits, and we have looked at the latch, which is made up with NAND gates. That is all for now. See you in the next class.